Is this a number line? What is about to begin? Whoa, what is this? The number line is changing. It's moving in a strange way.
Here, we're changing a parameter called Q.
Huh? Who are you? What exactly is this Q? Oh wait, the number line has returned to normal. And then it disappeared. What was that just now?
Zundamon, I understand the situation now.
Metan, why are you here?
It seems that through the parameter Q, you saw a mysterious world.
You figured it out so quickly. I knew it. You're amazing, Metan.
What exactly is Q? Let's take a closer look. First, let's take n as a positive integer, that is, a natural number. A natural number can be obtained by repeatedly adding 1.
If you add 1 n times, you get n. Well, that makes sense. It feels kind of obvious though.
This is where everything begins. If we introduce a parameter q into the natural number n, we obtain an analog of n.
What is this? You add q to 1, then add q squared, and it goes on up to q to the n minus 1.
Yes, it's summing n terms obtained by multiplying 1 by q step by step. If we set q equals 1 here, the analog of n coincides with n. This number, which resembles an integer, is called a q integer. As a note, for now we are only considering the q integer corresponding to positive integers.
A q integer. It sounds kind of mysterious.
Here we can think of the integer as being deformed through the parameter q. Alternatively, the integers we know can be seen as a special case of q integers.
That sounds complicated. So a q integer is a generalization of an integer?
That's right, exactly. Let's actually try transforming natural numbers through the parameter q. Then it turns out like this.
Oh yeah, it looks kind of similar to what I saw earlier, but it feels like something is missing.
That's because we're only seeing a small part of the world of q integers so far. First, let's extend q integers so they also correspond to negative integers.
But earlier we defined the q integer of n as having n terms lined up. Then if n is negative, I'm not really sure how to think about it.
You're right about that. So here's what we'll do. First, let's multiply the q integer of n by q. Then, 1 becomes q. Q becomes q squared. And finally, q to the n minus 1 becomes q to the n.
I've seen this kind of calculation somewhere before.
Now let's subtract the lower equation from the upper one. So on the left we can factor out the q integer of n, and it looks like this. Meanwhile, on the right side, most of the terms cancel each other out. And what remains are just 1 and q to the n.
You're right.
Then, if we divide both sides by 1 minus q, the q integer of n can be expressed like this.
I thought it looked familiar. This is the sum of a geometric series.
Good observation. Yes, exactly. What we're calculating here is the sum of a geometric series with initial term 1 and common ratio q up to the nth term. Anyway, putting that aside, this time let's take this formula as the definition of the q integer. Unlike before, this definition allows us to calculate even when n is 0 or negative.
Oh, so this form has that kind of advantage.
I'm glad you understand. For example, what happens to the q integer of 0? Can you figure it out?
Okay. According to the definition, the numerator includes q to the power of 0. Since q to the 0 equals 1, it ends up being 0.
Yes. We can see that the q integer of 0 is always 0, regardless of q. Now, let's continue. Here, if m is a positive integer, that is, a natural number, the q integer of m can be expressed as the sum of n terms, just like in the original definition. And for the q integer of minus m, I'll explain the reason later, but for now, the result can be written like this.
Oh, I see.
However, when considering the q integer of minus m, we must require that q is not 0 to avoid having 0 in the denominators.
Got it.
Just like the q integer of n has m terms, the q integer of minus m also has n terms. And as q approaches 1, each term approaches 1. Since there's a minus sign here, as q approaches 1, the q integer of n approaches n. This holds true even when n is negative.
Huh? So instead of substituting q equals 1, we make q approach 1?
In the definition of a q integer, the denominator contains 1 minus q. So to avoid making the denominator 0, we take the limit as q approaches 1 instead of substituting q equals 1 directly.
Aha, I get it now.
By the way, we already confirmed that the q integer of 0 is always 0 regardless of q. But what about the q integer of 1?
According to the definition, the numerator includes q to the power of 1. That means the numerator and denominator are the same. So the answer is 1.
Well done. Yes, the q integers of 0 and 1 match their original integers regardless of q. These two are special cases, so it's worth remembering them.
I'm not sure what they'll be used for, but I'll remember them anyway.
And with this, we can now handle q integers for negative integers as well.
That sounds cool.
By the way, when q approaches 0, the q integers for negative integers diverge.
They shoot off to negative infinity.
Now, this is where things get interesting.
Really?
Let's extend our stage to the complex plane. For a point, x, y, we associate the complex number x plus yi. That was what we call the complex plane.
Oh yeah, I think I've heard of that before.
Now let's extend q to be a complex number. As before, let's represent q as a red point. And when we move q...
Whoa, what's this? This is what I saw at the beginning of this video.
Ah, you just said this video, didn't you? If we naively extend our discussion from integers to real numbers, then the entire set of real numbers, that is, the whole number line, can be deformed like this.
Wow, that's amazing!
Strictly speaking, a complex number raised to a real power does not have a single definite value. So we choose a representative value called the principal value. If you don't quite get it, feel free to just ignore it.
Okay, I'll ignore it.
Furthermore, when q is a negative real number, the integers return to the original number line as special points. However, their order becomes scrambled.
It's spinning like crazy back there.
Also, when q moves along a circle of radius 1 centered at the origin, the so-called unit circle, we can see a fascinating shape.
The number line has transformed into a circle. Huh? There are only 6 points left.
Depending on the value of q, infinitely many points can overlap, so only a finite number of q integers may exist. Well, that can be considered a special case.
It's strange to think that there could only be a finite number of integers. By the way, can we actually calculate with q integers? Can we add and multiply them like usual numbers?
That's an interesting question. What happens to addition and multiplication in this twisted world of numbers? What kind of operations could be considered natural additions and multiplications for q integers? Let's investigate that. But before that, as we've seen, when q equals 0 or when q lies on the unit circle, that is, when the absolute value of q is 1, these are special cases, so for simplicity, let's exclude them from our discussion.
Understood. Alright, let's try adding q integers first. To begin with, we'll use q integers that correspond to natural numbers. Each q integer for a natural number is expressed as a sum of powers of q, right? So here, each one has the same number of terms as the original number.
Unfortunately, it doesn't seem like we'll get the expected result if we just add them like this.
What do you mean?
What if we multiply just this part by q to the 5th power?
You mean like this?
Exactly. In that case, multiplying by q step by step gives terms up to q to the 7th.
Wow, that's awesome! This corresponds to the q integer of 8. In other words, it's the q integer of 5 plus 3. In this calculation, we adjusted the q integer of 3 by multiplying it by q to the 5th power. So in the world of q integers, this kind of calculation holds.
That's quite an interesting result. The addition of q integers is quite similar to usual addition, but we adjust the value using q here. Then we get a result that corresponds to usual addition.
Yeah!
Let's look at the general case. What happens if we add the q integers corresponding to integers n and n in the same way?
Okay. Here, n and n are not necessarily natural numbers, so we have to consider the case when they're negative. Then we'll need to use this definition.
That allows us to handle negative integers as well.
Alright, let's keep calculating. The part multiplied by q to the power of m looks like this. Now, since both fractions have 1 minus q in the denominator, and the q to the m terms cancel out, it ends up like this. This represents the q integer corresponding to m plus n.
We've arrived at the result. Based on this result, let's define the addition of q integers like this. This symbol represents addition for q integers, while the other one represents usual addition.
So the addition of q integers is defined in terms of usual addition, but there's a shift involved here.
Yet, the result still corresponds to usual addition. In that sense, this addition for q integers can be called natural. By the way, note that this symbol can have different meanings depending on the field. Also, at first glance, this definition may look asymmetric in m and n. But as you can see from the result, it's actually symmetric with respect to n and n. That means swapping n and n doesn't change the value.
That's such a strange definition.
As a special case, what happens if we add the q integers corresponding to minus m and m? Well, let's assume n is positive.
Hold on a sec. Since q integer addition corresponds to usual addition, this should be the q integer corresponding to minus m plus n. Looking closely at this equation, the left-hand side can be written like this according to the definition of q integer addition. And the right-hand side is the q integer of 0. We already confirmed earlier that it equals 0. So that means the q integer of minus m can be expressed in terms of the q integer of m like this.
That's an interesting result. In fact, when we expand the q integer of m, we get an equation like this.
That's the one we saw earlier.
Of course, you can also calculate this directly from the definition of q integers. If you're curious, try it yourself.
So you're saying it's one of those left to the reader things?
Now that we've done addition, let's move on to multiplication. Try calculating this expression.
Got it. Huh? Something looks strange here. It's not q, it's q to the 4th power.
We're short on time, so I wrote it that way from the start.
What do you mean? Well, whatever. Let's just try calculating it. According to the original definition, the q integer of 4 can be written like this. And the q integer of 3 is? Wait, since it uses q to the 4th power, maybe I should call it a q to the 4th power integer? How should I think about this?
Think of it as adding up terms where you multiply 1 by q to the 4th repeatedly instead of by q. Since we're looking at the analog of 3, there will be 3 terms.
Ah, I see. Alright, let's expand the expression. Okay. First, expanding this part gives this result. Then, expanding the next part gives this. And finally, it becomes this. So this means, since we have terms from 1 up to q to the 11th, this is the q integer corresponding to 12. That is, 4 times 3.
That's cool. In the general case, it gets even cooler.
Oh, really? Alright, let's try calculating this one too. Then I'll use the general definition that includes negative integers. Then the q integer of m looks like this. As for n, since it uses q to the n power instead of q, should I think of it this way? Here, I replaced q with q to the n power.
That seems right.
The 1 minus q to the n factors cancel out here. So that means, it simplifies to this. Which means this is the q integer of nn.
Well done, Zundamon! Surprisingly, multiplication turned out to be easier to calculate than addition.
That ended more quickly than I expected. Though it's a bit unexpected that we use q to the n power instead of q.
Based on this result, let's define multiplication for q integers like this. Just like with addition, multiplication of q integers is defined in terms of usual multiplication. Be aware that this symbol can also mean different things depending on the field.
The difference from usual multiplication is that one of the q's is replaced by q to the n power. Since they use different q's, it feels like we're multiplying two numbers from different worlds, but somehow the calculation still works.
It's kind of mysterious. Looking at the result, it's symmetric in m and n, so swapping m and n doesn't change the value in this definition. So it seems best to define the natural addition and multiplication of q integers in this way.
At first, it looks strange, but once you calculate it, it really works.
Both operations ultimately correspond to usual addition or multiplication, But these definitions make the internal structure explicit. Calculations with Q integers are very similar to those with usual numbers, but there are shifts expressed through Q. And as Q approaches 1, those shifts indeed disappear. These are interesting as deformations of addition and multiplication.
Yeah, I don't really get it, but that sounds right.
In general, a mathematical object or concept extended by a parameter Q is called a Q analog of the original one. Although today's topic can be extended beyond just integers, Q integers are the most basic and important example of Q analogs of numbers, so we focused mainly on integers for this explanation.
Integers are important, after all.
In the world of Q analogs, Q integers appear frequently. In other words, they are fundamental building blocks in Q analog theory. We couldn't go that far this time, but maybe someday we'll take on that challenge.
Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.